Bismillahirrahmanirrahim. Alright, class, Assalamu alaikum and welcome to the second lecture of week 9. And in the last session, we were trying to give some, background motivation or maybe some philosophy of why we should define potential when we have already discussed work done so far. So we said that, or we should say that, if you could recall when we were discussing Coulomb's law, we said that Coulomb's law gives us force experienced by two charges in its vector form, magnitude and direction both. And from this definition of force, we defined electric field intensity, and we said that if we want to find the electric field intensity of one charge, and in that definition of electric field intensity, only that charge should be present, other charge should not be there. So the definition should be absolute in terms of the charge for which we want to find the electric field intensity. So the other charge should not be there. Okay, so in order to standardize the formula or standardize the definition of electric field intensity, we said that electric field intensity is nothing but force experienced by a judge charge which is of +1 coulombs in the field of the source charge. All right, so the charge which we removed, actually we not removed it, we replaced the charge which we normally call test charge. So we removed that charge for which we did not want to know the field, and we replace that charge, test charge, by a judge charge which is +1 coulombs. And so the charge which was remaining now offers us the force that would be experienced by the judge charge which is of +1 coulombs. So if I write +1, so +1 here, so I can simply write QS. So now this definition, this is actually the force field. We all know that this is actually the force field, but now this formula involves only the charge which is the source in whose electric field intensity we are interested in. Okay, so this is now more standardized definition. So when we were discussing this definition, we also discussed about the philosophy of why we did that, and we took an example of some hypothetical experiment run by Dr. Abdurrahman Javed, and we are residing on some planet, and I sent 2 of my students. So same analogy, same motivation, or same I should say experiment I discussed about. I gave you the description of in the last session, at the end of the last session, and what I want to do, I want to now relate that we have so far found out the expression for work done. So how can we relate it? Work done is nothing but energy. How should we relate this work done to the potential difference or potential energy, which is more important for us, because this potential energy or potential difference is the one which gives us the characterization, or which characterizes the field itself irrespective of the charge which is being moved within that field, just like in the case of Coulomb's law and electric field intensity. Okay, once we got rid of the charge which we were moving in the field of the charge in which we were interested, we got the electric field intensity. So we defined electric field intensity as the force experienced by a judge charge which is +1 coulomb. Okay, that force is electric field intensity. So similarly, recall the description of the experiment we ran yesterday for Earth and Jupiter. I sent 2 students, one on Earth, one on Jupiter, and asked both of them to use one judge mass, 1 kilograms, to plot the field of energy around that planet, and try to note how much amount of work is required, or how much amount of energy is required in your planet, in your respective planet, to move a mass from height h1 to height h2 and plot this throughout the three-dimensional space around that planet. So work done is something uh, we had already discussed, gave an analogy in the case of Earth and Jupiter. Now let's translate that here. In the case of electrostatics, we know that the work done in moving a charge within the field of some other source charge whose field is given by E from point this to point that is given by this expression. Okay, so work done moving this charge from this point to this point in the field of some source charge. So how about if we want to quantify the work done? What if we try to standardize this definition, just like we standardize this definition for a +1 coulomb charge, and we said that now this Coulomb's law is electric field intensity. So instead of saying that work done in moving this charge within this field, how about if I say that work done in moving +1 coulomb judge charge in the field E, and this E field is for some source charge from point initial to final. This standard amount of work which we have to do in moving a charge +1 charge. Now I have replaced this Q by +1 coulombs. So the work done in moving a judge charge from this point to that point in the electric field is given by this. So this should have some special name to it, just like here we gave it electric field intensity. So we'll call it that work done as potential difference. So if the initial point is point B, as we normally take, and final point is A, so the potential difference between these 2 points A and B is actually the amount of work done in moving a +1 coulomb judge charge from point B to point A in the field of some other source charge Q. Okay, so now if you want to define energy field surrounding any charge distribution, so that definition of energy surrounding any charge distribution which produces electric field intensity should be independent of the amount of charge which is being moved within that charge arrangement which is actually producing electric field intensity. Okay, otherwise if someone would use, for example, we have a source charge of 10 microcoulombs and we want to quantify the potential field produced by this charge, and let's say we have got another charge of 100 millicoulombs, and now we want to quantify the potential energy of the field produced by this charge. So potential energy of the field produced by this charge will definitely have smaller magnitude as compared to this one, but if someone uses considerably high amount of test charge here and considerably low amount of test charge in this case, so if you use the formula for work done, this one, to quantify the energy to move this test charge and this test charge, so the results will suggest that the potential field of this source charge is considerably weaker as compared to this one, which is contrary to the fact. So it is really important to just as in the case of Earth and Jupiter's case. So we have to definitely define or standardize this judge charge, just as we did standardize the judge mass to be +1 kilograms. For the experiment to be meaningful, for the results to be meaningful, we should also standardize this judge charge. And we said that this judge charge is going to be our normal definition of the judge charge, that is +1 coulomb judge charge. If we want to make it +1 coulomb, what we are doing actually, we are dividing this work done by this Q, and now this is still the amount of work done, but still amount of work done in moving the judge charge within this field. This was amount of work done moving this charge. So although it is work done, although it is energy, but this is now standardized to characterize a particular field produced by source charges or source charge distribution. Similarly, just like the case of electric field intensity, this is still, E is still the force, just as Coulomb's law, but force experienced by the judge charge, within the field of source charge was electric field intensity. So the amount of work done in moving the judge charge from point B to point A within the field of some source charge distribution would be energy, but would be work done, but a special name which we'll call potential difference. So potential difference between B and A. So after standardizing this, I should better write formula for potential difference now between 2 points to be closed loop line integral of E dot dl. Let me call it equation number 4. So if I take equation number 3, this was the work done in moving a charge Q within the field of an infinite uniform line charge density rho n, where B was the initial point, A was the final point. So if for this case of infinite line charge distribution, I want to find potential difference between the 2 points, what I have to do is simply divide this work by the amount of charge, the charge which we were moving within that field. Or in other words, what we are doing, we are replacing this Q by the judge charge of +1. So +1 कभी भी equation में नहीं लिखा जाता, so we never write +1 in equation. So what we'll have is this. So now we have got a formula for for potential difference. Let me call it equation number 5 now. Potential difference within the field of an infinite uniform line charge density. So potential difference for infinite uniform line charge density is given by this formula, ln B upon A. So this is equation number 5. How about if we had a point charge and we want to how about we had point charge Q as the source and we want to find the potential field surrounding it. We already know that if we have a point charge normally, so it's best to keep that point charge at the origin of a spherical coordinate system. And if we would do so, this point charge, which is the source charge, will produce an electric field intensity of Q upon 4 pi epsilon naught R square AR, where this AR has got a specific meaning. It is primitive unit vector of spherical coordinate system, and this R is first of the 3 coordinate variables. So if I want to find the potential field surrounding this charge, I can use the formula for potential difference between 2 points A and B, VAB, the formula which is given by 4 is equals to minus under root from B to A. So let's say that there is a point B and a point A, okay, and let's say these points are lying on the radial line. So the unit vector which is locating point, not unit vector, the position vector which is locating point A is, let's say, RA, and the vector which is locating point B is, let's say, RB, the position vector which is locating. So instead of BA, I should replace positions of these vectors, okay, positions of these points. All right, so instead of B, I am writing RB, and A, but I am replacing by RA, position vector RA. So equation number 4, E is given by this: Q upon 4 pi epsilon naught R square AR dotted with DL. DL in spherical coordinate system we all know is dr AR plus r d theta a theta plus r sine theta d phi a phi. This is the formula for DL. So if we are taking this these points along a radial line, so definitely only radius will change and the two terms will be 0. So instead of DL, I can write dr AR. So if we evaluate the dot product, what we'll get, and we are keeping the constants out of the integral sign, so Q constant, 4 pi epsilon not constant, dot product AR dot AR will be 1. So in integral sign will be left with RB RA, with an integral sign will be left with dr upon R squared. Okay, so if that's the case, so the potential difference between point A and B for a point charge potential difference between A and B for the field of a point charge is given by minus Q upon 4 pi epsilon naught. Integrate, if we integrate this, what we will get is minus 1 upon R, is it? Is this what we are going to get? Okay, take it above. Okay, yeah, this is what we are going to get, but I'm just writing the equation, the result directly. You can, after integrating it and replacing the limits, what you will be left with 1 upon RA, 1 upon RB. So definitely you can take R square in the numerator, so it will be R raised to minus 2. So you can easily integrate this one. So not a big deal, so I'm not doing it here. I'm just showing you the last, sorry, R B minus RA. It would be like RB minus RA, okay, after putting the limits. So if you take the minus sign inside, you'll be left with RA minus RB, okay. So this is the potential difference for a point charge which is given by Q. All right, so For a potential difference between 2 points within the field of a point charge, the formula is for q upon 4 pi epsilon naught 1 upon Ra minus 1 upon Rb, where Ra is the unit vector, Ra is the length of the position vector locating point A, and Rb is the length of the position vector. This is not the position vector as a whole, length of the position vector locating point B. Okay, this is length. I haven't shown any bars over it. Okay, definitely potential is an energy, so there should not be any unit vector or vector in on the right hand side of all the equations from equation number 4, 5, 6 and so on. So one might argue that, sir, you have chosen DL to be on a radial line. What if or the initial point and the final point on the same radial line? What if B was here or B was here and point A was here or somewhere else? In that case as well, if let's say this is the position of the initial point, so the unit vector, the position vector locating point B will be Rb. The position vector locating point A is again Ra. You can also change point A, but the position vector will remain the same. So when you will use this formula, okay, to find this formula for electric field intensity, and use equation number 4 to find potential difference between 2 points which are located by Rb and Ra. So even after that, what you'll have to do now, this time earlier when we derived this expression, we chose B and A to be on the same radial line. But if we are not doing so, if we are generalizing thing, so this time we cannot take it to be 0. D theta A theta r sine theta d phi and so on and so forth. So now we cannot make any term 0 now, because our journey from point B to point A, this is our initial point, this is our final point. We are now taking the jet charge from this point to that point within the field of the charge which is placed on origin, source charge. Okay, so for this source charge we have got this electric field intensity. Now this direction of motion, the direction in which we moved, now may have all the 3 components, but nevertheless when you'll use equation number 4 and you'll take the dot product of E dot dl, since electric field intensity has got only AR component, so this E when dotted with D, the first AR component, it will be this. When it will be dotted with the rest of the 2 terms, so it will be like AR dot A theta plus some QS upon so and so, and AR dot A phi. So we know that AR and A theta and AR and A phi are orthogonal to each other. We have already discussed in spherical coordinate system that all these 3 unit vectors are orthogonal to each other. So even if you consider this DL and put as a whole in equation number 4, since electric field intensity due to a point charge has got only R component, if you take the dot product, only R component of DL will remain and the 2 components will be 0, merely due to the fact that AR and A theta are orthogonal, AR and A phi are orthogonal. If you want to do, you can do it and confirm what I'm saying. At the end you'll get this expression again and this expression again, and integrate it, you'll get this expression again. So equation number 6 is still valid. Okay, whether you choose the points to be on a same radial line or on different points. So what does this gives us? This irrespective of changing the points earlier on the same radial plane, now on different, as long as the length of this position vector RB and RA remains the same, what will have? Will have the potential difference between those points the same in case of a point charge QS at origin. Why is it so? Because field of a point charge is also conservative field, so it does not matter whether you take a point charge from here to here in a straight line, or you deviate in random fashion and stop here. As long as the initial point and the final point are equidistant from the source, you will get this same result, equation number 6. So you can also move this point from here, a point charge, jet charge from here to here in a straight line, or making some random fashion starting from B, moving around and randomly and place the charge here, the work done will remain the same. So again, if the work done is independent of the path followed and it is only depending upon the initial point and the final point, we say that such fields are conservative fields, right? We had discussed this previously when we were discussing line charge, and we said that if electric field is constant, meaning if electric field is produced by an infinite sheet of charges, and if you try to move a charge from point B to point A, all right, in that case we showed that the work done was independent of the path followed. Again, in the case of point charge, although this is not a constant field, this field is depending upon the distance. Farther you go from the source, lesser would be the magnitude. It is not constant, but still our results are the same. It says that as long as you are maintaining the distance from the source the same, it does not matter in which fashion you move your jet charge from an initial point to final point, the work done would be the same. All right, so this is all about potential difference. So actually this is giving us the potential difference between 2 points. So how about potential itself? So what's potential, or in other words, absolute potential? Saying potential also means absolute potential. Absolute potential is definitely something which is absolute, which should not be with respect to something else like potential difference. Okay, potential difference is definitely asking us to find the work done in moving a charge from this point to this point. So this is the potential difference. But how about absolute potential of a point of the point B or point A? Okay, we can find potential difference moving a charge from this point to this point, moving a jet charge from this point to this point as potential difference. But how about potential at this point? Just like, let's say this is the Earth's surface. Okay, if you have a mass here m, 1 kilograms, and you want to move this from by a height h. Okay, so now the here potential was potential PE1, here potential was PE2. So the potential difference between these 2 points is nothing but P2 minus PE1, or mgh. Let's say this height is h. So this is the potential difference. So how about potential of this point itself, or potential of this point itself? When the mass was here, was the potential 0? No, it had some other value. When the potential mass was here, was the potential at that point was 0? No, it had some value. But we calculated potential difference using this formula. So now we are in the case of electrostatics, if the charge is here, so the potential at this point is 0? No. If the charge is here, the potential at this point is 0? No. I am talking about electrostatic potential. The potential is not 0. Okay, but we have calculated a way to calculate, we have found out a way to calculate the potential difference between these 2 points. So that is potential difference. But how about absolute potential of point B or absolute potential of point A? So absolute potential is always calculated from some reference point where the potential from that reference point, that the characteristic of that reference point is that the potential at that point, which we are considering as reference, has got 0 potential. Okay, so if I want to find absolute potential of this point, which is PE1, so I'll have to calculate the potential at this point due to some reference over which the potential is 0. So definitely in case of Earth, we know that if we know this height h1, we can calculate the potential at this point using mgh1 formula. Mgh1, the absolute potential at this point is mgh1. Why? Because this h1 is now calculated with respect to some reference point over which the potential is 0. If a mass is lying here, so the potential is 0 obviously. Similarly, if I want to find the absolute potential of this point, so for that I'll have to calculate the distance or height of that point with respect to certain point over which the potential was 0. So what will have mgh2? It means that absolute potential or at this point or this point is nothing but work done in moving the judge mass from a point over which the potential is 0 to the point of interest. So the amount of work which we needed to do to move the mass 1 kilogram from Earth's surface to this height h1 gives us the potential, absolute potential of this at this point. Similarly, the amount of work which is required to move this judge mass from surface of the Earth where the potential is 0 to the point of interest, which is this h2 height above, is how much? mgh2. So the amount of work from some reference point over which the potential is 0 is not absolute, is not potential difference, rather it is absolute potential. So it means that if somehow we make here, if I want to find potential, absolute potential at point A, okay, so what I can do a little bit change in this formula. Start from some reference point and place the judge charge at the point of interest, and now this potential difference formula has been converted into a normal in an absolute potential formula. Now this formula is generic for potential difference. Now this is for absolute potential. Why? Because the initial point has been replaced here to be the reference point, and it's common sense out. It's implicit that reference point is the point over which the potential itself is 0. Okay, so okay, now so if in the case, if let's consider question number 6, if I want to find the absolute potential around this point charge, equation number 6 is giving us the expression for potential difference, but I am not interested in potential difference, rather I am interested in absolute potential around this charge distribution, which is nothing but a point charge at origin. So what I can do, I can take a reference point, initial point. I should replace RB, this is nothing but the length of the unit vector which is locating the initial point. So this initial point should be located somewhere at some place over which the potential is 0. So if we have only one point charge and nothing else in the universe, then definitely the reference point over which the potential would be 0 is infinity, because at infinity field will be 0, so potential will also be 0. So if from equation number 6 I just replace, if I want to find potential at some point A, VA, so the I'll have to replace RB, that is the length of the vector locating the initial point. And if I'm interested in absolute potential, so the initial point is at infinity, so RB is infinity. So the formula for absolute potential at point A within the field of a point charge will be given by RA. That's it, because RB has been replaced to be infinity when upon infinity is 0. Wow, great. So if I just remove these subscripts, so potential at any point surrounding a point charge is given by this very important formula, and let me call it equation number 7. All right, so this is equation number 7. So okay, now this is equation number 7 is the formula for finding absolute potential surrounding this point charge, and equation number 6 is the formula for, or is the field for, a scalar field for finding the potential difference around this point charge. All right, now it is not necessary that field is always 0 at infinity. Yes, it's true, but most of the times we won't be able to take infinity as our reference point. For example, if in the case of equation number 5, where we had an infinite line charge density on z-axis, if I want to replace, take infinity as the reference point, so I'll have to put b infinity, so I won't be getting anything out of this. So we should remember, again, gravitational field, point 1 has got absolute potential PE1, point 2 has got absolute potential PE2, and remember absolute potential, so we are taking these potential with respect to some 0 reference. Okay, so the potential difference delta PE, potential difference is nothing but PE2 minus PE1. Similarly, if we because the definition of potential and potential difference in gravitational field is the same as we have been defining in electrostatics. So potential difference between 2 points, point 1 and 2, or if to be more consistent, let me just give this point B and point A. Okay, so potential difference is potential energy at point A minus potential energy at point B, initial point, final point. Okay, so if that's the case, potential so that analogy can be applied on electrostatics as well. So potential difference between 2 points in electrostatic field can be written as the difference of absolute potentials as well, just like in the case of gravitational field. Okay, so let's say this is the point charge located at origin, source charge. Okay, so this is point B, let's say, and this is point A, let's say. So the amount of work done in moving a positive 1 coulomb jet charge from infinity to move a positive jet charge from infinity to this point B is VB, absolute potential at this point. And the amount of work done to move a positive 1 coulomb jet charge from infinity to this point A in the vicinity of this source charge QS, that amount of work is given by absolute potential VA, and potential difference between these 2 points is given by VAB. So this VA, VB and VAB are related by this formula, can be related by this formula. You can think of this example as analogous to this one, as analogous to that one. Okay, so now it means that if I want to use this formula, definitely I cannot put B to be at infinity. For that, there is another method. What we can do is equation number 5. From equation number 5, if we want to figure out the absolute potential within the field of infinite uniform line charge density, so if we want to do it like this, so VAB is nothing but rho L upon 2 pi epsilon naught ln B minus ln A. I think I can write it like this, where this was initial point and this was final point. So what I can write is minus rho L upon 2 pi epsilon naught ln A minus rho L upon 2 pi epsilon naught ln B. This is what I can write. Okay, so what I can do is I can treat this, which is the absolute potential at point B, I can treat it to be some constant. Okay, so we should always remember, okay, if I just remove these brackets, what I'll have to do, I'll have to place a plus sign here. Okay, so remember that this is VA and this is VB according to this definition. So what we can do is, since we cannot take B to be infinity and consider VB to be 0, because if we will do so, we'll get an indefinite number here. So what we can do for this case, we can consider that, okay, VAB is equals to minus rho L ln A divided by 2 pi epsilon naught, and this potential is some constant potential, definitely, at some reference point. And from the situation, there may be some situations over which we can see that potential difference, potential at some reference point, not difference, at some reference point. If you have, what we have done now, we have taken this potential difference from this expression, from equation number 5, this expression, from this to this expression. So this is absolute potential at point A, this is absolute potential at point B, which is which we don't know, because we cannot put infinity here, and if we would put infinity, this would be 0, Okay, but now we are not able to put infinity because we won't be able to get any legitimate term for the second this term. So we can put some other value. If we would put some other value other than infinity, we will get some constant value for voltage at point B. We are calling it C1, some constant value. Okay, and now from the problem, from the charge distribution, try to figure out that what would be the voltage at any point within that charge distribution. Okay, let's say we want to take a point now. Here the only variable is a. Okay, now let's say if we want to take, just for the sake of argument, let's say we want to take a to be, let's say a1. At a1, let's say let VAB be 0. Okay, we are arbitrarily assuming this. Okay, but we'll have to take this information out from the problem which is given to us. In that case, what we'll have 0 equals to okay, not 1. Maybe it is not good idea to take 1. So let a at equals to 2. At a equals to 2, let VAB is 0. So in that case, if I would replace these values here, 2 pi epsilon naught ln of 2 plus c, just and not 0, some other value, because 0 is not in the case of infinite line charge. In the case of infinite line charge, the field is 0 at infinity, so we cannot take the charge to be infinity, the potential to be 0. We will have to take some value, so let that be 1. So now cross multiply this and find the value of C1. Okay, once you get the value of C1, you can find the potential at any point, absolute potential. So I just wanted to give you a rough idea how to select a point to be a reference if the reference cannot be infinity. So that's all for today. Assalamu alaikum.